Hi, in today's video, we'll be going through another type of generating function known as the exponential generating function. In the previous video, we went through ordinary generating functions to help us solve distribution problem from identical to identical, but it can also help us solve other type of problem. For exponential generating function, it is useful when we want to count ordered arrangement now, like permutations. And so, unlike the ordinary generating functions they define for the sequence of x squared, x cubed, the coefficients now are of the form of the power series a1 x over 1 factorial plus a2 x squared over 2 factorial. And the reason for that is because if all of these coefficients are 1, you get back ex, e to the power x. And that's why it's called exponential generating function. We'll see later how it can be used to count ordered arrangements. But we'll continue now with some common EGF. As I said, if all of them are 1s, it's just e to the power x. Now, if your sequence of numbers is a permutation of the r terms, then it's 0 factorial, 1 factorial, 2 factorial, r factorial. Then you just get back 1 plus x squared all the way 1 all the way to infinity, and that equals to 1 over 1 minus x. Likewise, if it's 1k squared, k to the power r, then that will be e to the power kx. And you can just write them down and you can see for yourself why. Now, if we want an alternating sum with 1, 1, minus 1, 1, then it's just e to the power minus x. If we want the even power terms only, means we want to kill off, we just take this e to the power minus x and we add back with the original. So this minus x will cancel out with this plus x. This minus x cubed over 3 factorial will cancel out with the plus x cubed over 3 factorial. And then because all the even terms are repeated twice, we divide by half. Likewise, for the odd, you just take e to the power x minus e to the power minus x, and then you divide by 2. So this allows us to play around with the exponential generating functions. And now let us see how we can model this exponential generating function. Before that, let me also say one note is that any operations that we have already went through in the ordinary generating function, such as when you multiply 1 minus x, all this, it is applicable to the exponential generating function, because it is applicable in a certain sense if you are able to change the division. Because if you now times x here, it will be x squared over 1, and that doesn't fulfill the condition that is over r factorial. So the operations might not be always relevant, but I hope you can play around with it to see what is needed for the problem. So let's move on to examples. One example and one use of exponential generating function is, like I said, it deals with order arrangement, and so we let our coefficient be the number of r permutation of identical objects now. Well, what does that mean? It means that how many permutations of an identical object can you have? Well, that's obviously one. You can only permute them one way, because like if you have A, and A, then the number of 2 permutation is just choosing these A's, which doesn't matter, so it's one way. And then you permute them, and because A and A permuted is still one way, times 1, so that's 1. So all the coefficients are 1, and that's why the generating function is in this form. You might think this is a trivial case, but we'll see why this case is applied on to later problems. So this is the general version of what we have just said. If we have identical objects, that means repeated, and we want to permute them, then for the first repeated one, it's just 1 plus x over 1 factorial plus all the way to x to the power n1 over n1 factorial. And then you could have chosen something from the other repeated object and move on. Well, this example is actually already seen in the first few videos when I teach you permutation and repetition. Because for the case of, let's say we have apple and we want to permute 3 of the letters, then we can write them as the multi-set accordingly. And we see p repeated twice, so we want to permute 2 of them. We actually use the way to break down the cases. And actually that is the only other way. And so this way of using the exponential generating function is so-called technically like modeling these repeated cases, and you just need to solve for the coefficient accordingly. And like I said in the previous video, from combinatorics, sometimes we want to get back into algebraic expressions that we can manipulate the coefficients easier, so that we do not always need to think of the algebraic problem, the combinatorics problem. And as we've seen in like video 4, if all these n's are infinity, then the number of permutation is just the first slot has k choices and the last slot has k choices, so it's k to the power r. And that coincides with our EGF version as well. Next application is when we want to distribute distinct to distinct boxes. But when we use permutations, each of these distinct boxes has to be either less than the objects or equal to the object, so that you have no empty boxes. But with EGF, it allows for empty boxes or not, and the ordering within the boxes does not matter in this case. That's why it's a distribution. You distribute something when you don't care about the ordering. And this problem is actually equivalent to having the number of r-digit n-ary sequences. What does that mean? It means your r-digit means you have a length. Let's say 3-digit, then it's just length of 3. And binary means it's 0 or 1. The standard one is a ternary, which means our 10 digits that we always use, but it could be any sequence. The boxes represent the digits because they are distinct. So let's take a simple example where our EGF for this case 1 plus x over 1 factorial plus x squared over 2 factorial to the power n. This just means that we have our r digit can repeat our n types of digit can repeat n times. Like, okay, so let's repeat this what I've said. So imagine you have r digits now. Then you can repeat your n type of digits infinitely many times. So each type of digit is 1 plus x squared over 2 factorial plus all the way. And you repeat this n times. Because you have you have n types of digit. And because they can be repeated infinitely many times, it's essentially e to the power nx. And so the coefficient is n to the power r, which is exactly the same, because in our combinatorics proof, how do we want to do this? Is if we have r digit, our first digit can have n options all the way to the rth digit. So it's n to the power r. You can take a look. If no box is empty, you just omit the 1 here, and it's just ex minus 1 to the power n. And it's actually just equivalent to the number of surjective mappings. You can read more about that online, and we'll move on to an example to further illustrate the use of exponential generating functions. An example will be like earlier, where now we want to our AR is the number of r digit quaternary, so 4 digits, if 4 types of digits, so there's 0, 1, 2, 3, and we have a R length digit number. And then because if we put in conditions such as each digit appears at least, the digit second 2 and 3 appears at least once, it makes it very hard to do a combinatorics proof because there are many cases to consider, such as like 2 appear, and then because it's R digits, it's quite arbitrary. But with exponential generating function, you can simplify this to an algebraic expansion, which is easier because now for the 1 and 0 digit, you can choose them. You have two. You can do them 1 plus x squared all the way, infinitely number of times. And then because it is 0 and 1, there's 2 of them, so it's 2 power 2. For the second and third, because now it appears at least once, you cannot have the option where you choose none of them. So 1 is disregarded, and so it's x plus x squared over 2 factorial all the way. Then there's e to the power x squared bracket ex minus 1 squared. And when you expand out, it's just e 4x minus 2e3x plus e to the power 2x. And each of these can be written as a power series that we have seen. And so when you simplify the power series, this will be the coefficient of AR, or x to the power r over r factorial. And this represents your AR. And so you can easily get a closed form formula for this problem. Now I'll do one example with you. So let's say we want to distribute the number of R distinct objects into 4 distinct boxes. As we have said earlier, it is equivalent to creating the number of R digit n-ary sequence. So it means we want to distribute R distinct objects, means R digit quaternary, because there's 4. So it's 0, 1, 2, or 3 dot. The digits representing the different boxes. So box 1 must hold even number of objects. So let's just say this is box 1 is for first digit 1. And like I said, even power is this exponential generating. So it's ex plus e power minus x divided by 2. So like it's ex plus e minus x divided by 2. And then box 2 must also hold even number, so that's squared. But they say box 3 must hold odd number, so that the digit 3 hold odd number. And lastly, the 0th digit can hold any number, so that's e to the power x. And if you expand out, this is just 1/4 bracket e 2x plus 2 plus e minus 2x bracket e 2x minus e minus 2x times half. So you can remove this 1/8. Then this will be e4x plus 2e2x plus 1 minus 1 minus 2e minus 2x minus e minus 4x. And so if you simplify this expression over here, it will be 1/8 bracket e to the power 4x plus 2e2x minus 2e minus 2x minus e to the power minus 4x. And then we just use the power series formula. So this e to the power 4x will become 4 to the power r plus 2 times 2 to the power r minus 2 times 2 to minus 2 to the power r minus 4 to the power r. So this gives us a formula for us to solve for this expression in closed form. And so the number of ways will just be 1 over 8 4 to the power r plus 2r plus 1 minus plus 2 plus minus 2r plus 1 minus 4 to the power r. And you can see how we have used exponential generating function to make our conditions easier to visualize and solve. And so you can use exponential generating function to model order arrangements. And I've hoped you have enjoyed this video because I've come to the end of it. Thank you for listening and feel free to explore more by yourself. Please like, share and subscribe. And this series will be coming to an end for counting. Thank you.